And that was how all the snakes were removed from Ireland. Happy St. Patrick's Day, guys. Unrelated to that, pre-calc, we missed a holiday. Which holiday? Pi Day. Okay, this is not a pre-calc class, but we have been talking about radians, and radians typically has what value in it? Pi. Are we going to do Pi Day in here too? It'd be super hardcore to eat pie for breakfast and then again for pre-lunch snack. Thoughts? Everybody in here, so it's pretty much Tolly and Delilah are the people that are... Do you guys want to celebrate Pi Day in here? Okay, all right, fair enough. Cool, so here's our problem. We have a diver who's standing on a diving board, and it's 3.5 meters long, and the board has a mass. Cool, it's supported in the middle and at the end, and obviously not the part where the diver jumps, right? Because if we're supported, it wouldn't do the springiness. As we're looking at this, we have to draw a picture. We have to make sense of it through a picture somehow. Now, whether we do the known first or the picture first doesn't matter to me. What do you prefer, Fern? Prefer, if you will. The knowns? All right, so we need to be really careful about the labels and stuff that we're going to use here, because keeping stuff straight is like the way through this problem. Can you tell me, Bea, one thing that I know that I might bother to write down? The mass of the diver. So I'm going to say M sub D. Okay, it's 85 kilograms, which that is a stout diver, but divers are pretty muscular, so that makes sense. Cool. Something else that I know, Delilah. All right, so I'm going to use a different L than I normally do. This is what my new L's look like because I think they look nicer. What do you want to use for board? L sub B? I'm fine with that. Equals 3.5 meters. All right, anything else? Totally.
14 kilograms.
Cool, so the mass of the board equals 14 kilograms. And there's a few things that we certainly could include. I don't know if we really need to. Do we have to write down gravity as 9.8 here? Or can we just work with the fact that we all know that? Second thing? Cool. All right, so I think this is really all that we have with one little thought here. We're trying to find the forces on the supports. Now, a picture will help. So let's sketch a small picture and see if maybe there's a couple more knowns that we can work out. So I'm not going to draw like a crazy good picture. Here's a diving board. It's fantastic. Now, if you've ever seen a diving board, typically on one end there's like ladder that goes up to it, right? I'm not going to draw the ladder. I'm going to call this E for end. And I'm going to actually put that label over here. So it's a little, what is going on here? There we go. I'm going to put it here. So there's the end. And then in the middle, they tell me that there's a support that's acting here. And I'm just going to draw it like this, make it a bold line. And there's a reason I'm doing that, but we'll see that here in a second. So here's a really bold line to show the support that it's connected to. And then over all the way on the other end is the diver. So at this end, we have a diver D. And here's our basic situation. You're looking at this, Riley, and you're thinking, no, I don't like it. But here's my guy getting ready to dive. And you don't have to draw this. Here's a sweet ladder coming up to it. And then here's a support that's stuck to the floor as well to hold the board in place. Okay. Is that cleared up? Okay. So here's my awesome picture. And we need to start thinking about all the forces that are acting on this thing, because there's quite a few of them. First off, if the diver's standing here and they're jumping or standing, their force pushes which direction? Downward, right? So this is the force of gravity that the diver exerts, and it's going to be pushing right here. Everybody cool with that? Force of diver. And it's due to gravity, but it's the force of the diver. Okay, so we could find that. That's that G value. I'm not going to bother writing that one. Okay, how about over here? And I'm going to get rid of my ladder just for a second. And this is the weirdest idea. If the diver's pushing down here, what is this support doing? So you want to say it's pushing up, and I get that, but our diving board has to be secured to this, right? Because otherwise the whole thing would just topple. So there must be some force through a bolt or something like that where tension's what's going to generate it. But there's another force that must be pulling down right here on the support. It's the end force that happens to be, it's connected here, and when it resists that turning, it's pulling downward. So this is the force of the end. support, which notice that's one of the supports that we're after. And then there's one more support here. Now, here's our third support, and I'm going to call this the center because they tell me it's the center of mass. So I'm going to label this as point C right now. And then there's a couple little weird things that happen here. I don't truly need that connected. It doesn't have to be connected to it because I'm connected at point E. Does the board have a mass? For sure. And anything with a mass is impacted by some field force that's generated near our planet. Gravity. So do you agree, just at first, that the board must be pulled downward onto C? I'm going to put it right here. Here's the force of the board. And I'm going to use C instead of B, just for the center. Okay, that's the force that C pushes down. Is there anything else? And I lied. I'm going to call that G, but that's an easy change. Force of gravity from the board. And then on the other side of that, my whole board doesn't tip like this, does it? It doesn't fall down. Which means even though it's being pulled down at C, that support at C that it's resting on must also do what? Louder? It has to push up as well, right? Like, even though it's just sitting there to like support it, it must be pushing up against it. Otherwise, everything would fall down. Are we squared away there so far? Okay. Now, it doesn't really look like we've added a ton of stuff here. I want us to think about the torque as well that's going on in this situation, which, remember, torque is just like the idea of force that makes stuff turn. And it's L sine theta, or R sine theta, however you want to think about it. Now, the nice thing is that this person is standing on a board and is perpendicular. If this person stood here, which way does it make the whole diving board want to turn? Downward. So in a positive or negative direction? So this is negative purely because it's clockwise. So here's the torque that's generated by the diver. On the other end, there's also a torque produced because theoretically this diving board shouldn't be spinning like crazy fast. That'd be a weird diving board. What direction does the torque over here at point E wind up going? Positive would be counterclockwise, negative would be clockwise. Positive. And it must be because check this out. E pulls down on this thing is what really happens. It's no different than if we have a weight on top. Here's the torque that's generated by the end. Now, the cool part of this is that because my center of mass is right in the middle of the board, is there any torque generated at C? Like if I perfectly balance a board here on this stylus, is there any torque that's being generated on the stylus or by the stylus? Like it's balanced, right? It's not turning. So we're good with this, I think. Okay, would it be helpful to measure some distances? Okay, so I think we know these. They're technically not just like given, but we can figure them out. Let's check here. The whole board is 3.5 meters, which means the distance from the end to the center, which I'm just going to call the length from the center to point E, would be what? 1.75. And I'm going to go ahead and include it here. The length to E from the axis of rotation or revolution is 1.75 meters. And I'm not trying to mix my colors, and I'm not doing it really intentionally, but they're getting all mixed up. Which means the length to the diver is also what? It better be 1.75 meters again. So I'm just going to say, I should have done it there, but length of the diver is also 1.75. Okay, there is a lot going on in this problem. But I'm pretty confident that we have everything that we possibly need with this. So now it's just a matter of kind of jumping in and trying to make sense of it. What is it that we're actually trying to find? And I'm going to do that one in this pink, purple. Is that pink or purple or both? Fuchsia? Let's just agree it's like right in the middle. Okay, what am I actually trying to find? Okay, can you be more specific? Because there's a lot of forces that I'm looking at here. Okay, so what would I label it? Force, what's the first support called? E. Good. Sorry, I just didn't hear you. So I need to find the force that's generated right here. So this force is what I'm after. And I need to find the force that's generated where? at the other support, at my center of mass right here. These are the forces that I'm after. Not gravity, these two. Now, I should see that they're in opposite directions. One's going to be positive, one's going to be negative. I can already tell that. And we are good to go ahead and kick in. Before we continue on, is there any part of this that anybody looks at and goes, oh, I don't really like it? Okay. When you did this problem on your assignment, I saw a lot of people make like a step or two and kind of trail off, which I totally get it. This is a hard problem. What, and I lied. How comfortable, how much do you remember with stuff? Should I give you a push before I say now work for a couple minutes? Okay, so let's just look at it. We're going to look at the equations and the work, and it's all going to kind of tie in together. I may wind up zooming out just so I can see it, but I'm going to start them right here so I can keep an eye on this picture as we get rolling with it. First thing that I care about, Mickey, have you ever seen a diving board spin around? Like, if I have a diving board and there's somebody standing on it, it doesn't just do this. It doesn't really spin at all, right? It just kind of stays still. If it stays still, it means that what do I know about the overall torque on this object if it's not rotating? It better be 0, right? So if we look at that, instead of saying the overall torque, there's a better way to write this out. The overall torque, how do we subscript that? Net. Nice. The net torque is equal to 0. I know that, and I'll plug that in here in a second. It's not turning. What are the only objects here that generate torque? Or, oh, so I heard Riley say the torque of the diver, so TD, and then I'm going to, before I write D here, I want to think this out. Positive or negative torque here? Negative, because we're going clockwise, right? So I'm going to put the positive one first. There's a torque generated by E. That's my positive. And then minus the torque generated at D. And I just rearranged it because I didn't want to write negative torque of delta first. Cool. Now, one more time, Nick, if my thing isn't moving, the diving board's not spinning around, what is the net torque? 0. So, if we want to show every little step, and I'm totally cool with it, I think that 0 then would be the torque at E minus the torque at D. Cool. Everybody still good? All right. There's one more little piece. This is a large part of the puzzle. What do you notice about the relationship between E and D? What should they have to be something? If they add to 0, these values must be the exact same, right? So last little comment I'm going to leave here. I know that the torque of the diver is exactly equal to the torque of the support at the end. There's my first little piece. Now, we're not going to plug and chug through this yet. We can if you want to, but I want you guys to do one more thing for me. Is the board moving up or down? Like we already decided it's not spinning, but as the person stands there, assuming that it's not like bouncing with crazy motion, they're just standing there. The board doesn't move up or down, right? Which means overall the net forces acting on this thing has to be what? 0. We're in equilibrium. So I'm going to switch color for this one very intentionally, but we also know that the net force is equal to 0, and we'll plug that in here in just a second. I want you guys spend a moment rather. I want you to write me out all the forces that are at work in this. Find me what my net force is the sum of. And I will give you guys a minute and I'll roll around a little bit here. I lied, I'll crutch around. So it's just however many there are, just add all those things up and you'll have fun. I mean, you can subtract if you want, but one of them is going to wind up being positive, right? Cool. I didn't pause it, so that's an awkward silence on that. No, you're good. The number of times I've come close to falling on Zeke's toys, just shooting out into my crutch, insane. Haven't yet. I'm sure it'll happen. I lied. The other day I stepped outside on my deck and it was icy on Saturday and I just totally ate it. Didn't hurt my foot. We cool. All right. How many things are acting? How many forces? There's 4 of them. Angel, can you tell me what those 4 forces are? Force of the end, plus the force of gravity. And I'm going to put a little asterisk here. Nope, not there yet. Any more? The force of the center and the force of the diver. Now, I'm going to put an asterisk above this one just to keep stuff straight in my head. Why? Something's different about C than all the others. It's positive. It's the only one that's pushing upward on this. Now, I'm going to go ahead and make one more. I'm going to pause this for a second because we're going to be able to move some stuff around. And I lied. We'll hold off on that. Okay. From here, we need to find a way. I see that FE is here and FC is here. So this equation is probably going to wind up taking us there somehow. I want us, and we're kind of bouncing back and forth, and I know that it's strange to do, but there's so much going on that if there's nothing obvious to do yet, like, I mean, I could write this and subtract and add, but I don't know really for sure what we have to add or subtract yet. So let's expand this. How do you find torque again? And we're going to just, here. How do we find torque? FR sine theta. Now, luckily for us, we're on a diving board, and any of the angles that are being generated are what? 90. So sine of 90 degrees, here's 0. 90 straight up here. What's the y value at the unit circle? 1. 1. The x value is 0, remember? So we're at 0 here and all the way up. Okay, so I'm not going to write the sine of theta because I know that it's 1 already. So that means that torque of the diver must be exactly equal to the force of the diver times, and now we could write the radius, but we called it LD, right? Or just, I'll use LD here, equals the force of the end times the length from the end, or the radius to the end. Now, there's a huge helpful part of this right off the bat that I see, and I'm hopeful that you guys do as well. Something really convenient about what we just wrote. They're the same, which means if I wanted to divide by LD or LE, which wind up being the same value, can I just divide both sides by it? And since they're the same value, when I divide by this 1.75 and this 1.75, we wind up seeing that the force of the diver better be the same as the force at E. Cool. Now, how does this right here play in here? And I'll even go one step further. This is an important statement that we're going to make use of. Why would this possibly matter? Oh my gosh, we can change. We could substitute in for either one of these, right? Now, as we look at it, we have to be really careful with this. And Bea, you're absolutely right. We can change one of them. Which one are we trying to find? FD or FE? FE. So what I'm going to do is I'm going to change this FD right here. I'm going to substitute this value right here with this because they're the exact same. And cleaning it up just a little bit, and I'll do it in 2 steps. The force of E plus the force of gravity, plus the force of C plus the force of E again. And I'm just doing a substitution here because I don't need the force of the diver. Okay, here we are. Thoughts? Anything that you see we can do? Yeah, let's just call it 2FE because I'm going to combine like terms. So one more little step through here, we get 2FE plus FG plus FC is still equal to 0. Now, remember that FC is the only one that's positive right now. So we can deal with that. All right. Well, thoughts? instead of just saying thoughts and awkwardly waiting, which is, a pretty common thing to do, I want you guys to play around with this for a minute. We are trying to find FE and FC. I've not done any calculations yet. We do have enough values to find something. Like, we could probably find FE right now, I think. Because I know the mass of the diver. And I know the gravity. Like, we could find several things. I want you guys to see if you can't rearrange this and solve for either FE or FC. I would solve for FE first because we know the mass of the diver, but it's your call. Cool. All right, I will give you guys like 2.5 minutes. Please ask questions when you have them. One approach is to try to solve this for FE, right? Solve this equation. You can isolate it and it works out. But the issue that you wind up with is if you don't know FE and you don't know FC, you can't solve one equation with two variables. So there's a roundabout in a way to kind of get it like through this maybe possible issue. I know that the diver's force is generated by gravity. That's the only thing that's generating it. Do I know their mass? I think so. What's the mass of the diver? 84. And they're accelerating. They may not be moving, but there is something acting on them.
I think it is 85.
Was it 85? Yes. You got me good. 85, and they're accelerating somehow. Something's pulling them down at 9.8 meters per second squared, or newtons per kilogram if you'd rather. Now, that's negative, right? It's pulling downward, which means the force of the diver is negative 833. Is that correct? Is it exactly 833?
Yeah.
Baller. And 833 what? Newtons. Okay, now this winds up being crazy, crazy helpful because that's not really anything that we needed, right? We didn't need FD. But what is this the exact same as? This is the same as the force at the end. So whatever that bolt is pulling on the board downward, it has to be at negative 833 newtons. Half the problem is now done. We have the force on the end. We only need one more force left. Now, I'm not going to plug it in until I absolutely have to, but I know this number. Could we find this number?
The mass of the board times gravity.
Yeah, it's the board that's being pulled down there, so I could deal with that. Could I solve this equation for FC? Like, that's a terrible question to ask, because yes or no questions just get a bunch of, like, subtle nods. But I think so. FC would be equal to what? Not number, just equation-wise. Negative, so I'm going to subtract them, right? Negative 2FE minus FG. But here's the really cool thing. Both of these forces, we have negative written here, and they're going in the downward direction, right? Which means now they're both made positive. Because they were down, I subtracted them. I never dealt with the negatives. But I now have that the force at C, and that's a strange comment to make just right off the cuff, and I want to make sure that we get that. Are you guys cool with why this changed to positive? They really were negative here. I didn't write them as negative, and then I subtracted them and said, oh yeah, they were negative the whole time. Cool. Well, we know FE, I believe. 833 plus Huggins said it was the mass of the board times gravity.
It's negative 137.2.
Wouldn't you do this one?
Yeah, but it's 14, not 15.
What's 14?
The mass of the
Gosh, that's the second time it's happened. Thanks for your patience. 14. Cool. All right. When we do these calculations, Fern, we just made eye contact. What did you get? 1803.2. And it's positive, which makes sense. Cool. I think we just found the force at the end, and we found the force at the center as well, how hard it must push up. These problems, this easily the hardest problem that we did, I think. I'm pretty confident of that. Okay, for these, just like pretty much any other math, like this is essentially a math class, right? It's applied math class is what this is. Try something as long as you're making sense, especially from the net torque or the net motion being 0, you always have an outlet through here. As long as you try something, you're probably going to stumble upon the right path. They're challenging. That's good for your mind. Cool. All right. Before we move on, if you guys have your computers with you, and I think this is the one time that I've ever done this, I want you guys to log on to your computers if you have them. If not, come grab your phone if you have PowerSchool on it. I want you to double check my grades that I have for you real quick. Are near the end. For this, how far did y'all get through the study guide? It's okay if like very little. Okay, here's kind of my thought. Today, I'm easing back into stuff just like you guys are. Here's what I think I would like. I hate these handouts because they don't always leave enough space to actually do stuff. So, today and tomorrow, we have like 5 minutes left now. I want you guys to start working through this. Okay, let's work solid 7 minutes right now. We are revving back into class. I want you to work on this till the end of class. Tomorrow in class, we will be continuing with this. Is anybody completely finished with this? And this is just going to give you like nothing to do for the next 80 minutes of class time? I guess 65 minutes, but cool. All right, so for the remainder of today and tomorrow then, I want us to go through this. I'm going to count this as a super low point quiz. It's just going to be take-home quiz stuff or in-class quiz. It's open note, open book. I'm not going to give you the formal test. I don't think it's fair, but I do think it's important that we at least look back and make sure like, oh yeah, this is everything that we learned before moving on. Cool. So give me like solid 6 minutes now as you're working on stuff, and I'll get some tunes playing. And there's no additional homework tonight. I will update the Google Classroom. Uh-oh.